I tried to collect a few things to show. So let's starting from Herschel Tau. These are the things that I've already shown. There were a lot of questions whether the azimuthal variations are to be lived. I mean, not the radial peaks, okay, but the features on top of the peaks, okay? Those are, one has to be careful with those, because since these are structures that are very extended compared with the angular resolution, the procedure of cleaning may introduce some artifacts. So one has to be careful on the small scale variation of intensity along a long feature like this one, okay? So one has to be careful with this. Not all of them are fully believable, okay? The other thing that I wanted to say, this is as also Phil mentioned, this is a very young object, okay? So this is a class 1 source, so there is still an envelope, it's still falling onto the disk. So this poses a number of difficulties also in the observations. You can observe relatively well the dust, because it's optically thin, essentially, the envelope in the dust, so you can see through. But it's difficult to observe the lines, and I have a slide on the lines in the next slide, actually. But first, the other thing is that since it's a young system, there is a lot of mass. The disk is very bright, and so the continuum of the disk itself is actually optically thick. So this one is I showed this already. This is the azimutally averaged, so the azimutally average profile, radial profile of intensity that shows the central peak and then the dark rings. Okay, this dark ring is this one, this second ring is that one, and then these two rings are these two rings. Okay. Since we have multiple frequencies at millimeter wavelengths, we can do a spectral index map if you want, and the spectral index map has this azimutally averaged radial profile again. And so you see that essentially where there is emission, the spectral index is essentially 2, okay? 2 is the spectral index of Rayleigh Jeans emission from an optically thick black body, okay? So this emission is optically thick. And so we cannot say anything about the dust property there. The spectral index drops significantly in the gaps, and this is probably because the optical depth is going down there, and so you start perhaps to probe the real spectral emission. But it's still difficult at this stage to to do an analysis of how much these values are solid, and whether we can say that there are large or small grains in these gaps. Better data, especially at longer wavelengths, for this purpose are needed, especially at 3 millimeter and with the EVLA. The 3 millimeter map that was in the paper and has been delivered with the data does not have the same angular resolution, obviously, has a lower angular resolution than this, so the gaps are less clearly visible in that 3 millimeter image. So, okay, so it will require some more integration time and some more observations to make sure of these things. So I mean, this clearly there is a lot to do in the future on this source. If you look at the lines, you don't see very much. The only lines that we detect are essentially these, which are in the 3 millimeter band. Okay, at the highest band we don't detect any line, and the reason for that, I believe, is because the sensitivity is not high enough, because we have a very small beam and the thermal emission from the line is not detected. Even in this band, we are basically severely limited by the optical depth of the envelope, because the envelope is very strong in these lines. So you basically, as you see here, these are channel maps and the lines, the contours overlaid with the continuum image, and we basically recover only a small fraction of the emission. And in fact, we do see the envelope when we look at the central star, at the central continuum peak, sorry, because we see the absorption of the envelope on the central source. So unfortunately, there is not much that one can really do at this stage with this data, with the line data, and there is not much more that I can tell you really on this. Another source that is interesting, boring. The one that I showed already yesterday is the one in which there was the detection of the snow line. And interestingly, there was this detection of polarized emission in the near infrared from the disk, excess emission, slightly closer than the snow line, and by one of you actually. And Antonio made a number of possible hypotheses on what this emission could be. And this obviously is surface dust on the surface of the disk, not on the midplane. And so basically this has to be caused by some variations in the dust in the upper layers of the disk that might be connected with something that happens inside the disk at the snow line. In fact, a new measurement of the snow line with N2H+, which is more sensitive, places it a little bit closer in than what was originally derived. And basically, you have it here in this plot on which Greta is working on that basically shows the snow line where we think it is now from N2H+ measurements. The excess emission in red on the two sides of the disk from Antonio, and then looking carefully at the Alma continuum emission at 850 microns, which is up here. So it looks very smooth if you look at like it. But if you look carefully, you see that there is an excess of emission at these two positions. And if you subtract a smooth distribution, you do see the residuals, which are two peaks of excess emission at 850 micron, more or less where the snow line of the CO is. So this might be connected with an effect of accumulating the dust or growing the dust or heating the dust near the snow line, which is something that is still ongoing. But I mean, these are preliminary results. Still, we are still waiting for additional data to confirm the nature of this emission. Another boring again disk that is not that boring, is this HD 100-546, in which in the inner region, the very inner regions, through again adaptive optics, it was detected the presence of two blobs, which you see them here, which could be possible protoplanets or young planets at a distance which is fairly large from the star, okay, I believe the distance of this blob here would be 50 astronomical units, so it's very large from the star. And Alma, as the Alma data is available now, still don't have the angular resolution to resolve these inner regions of the disk. You see here the blobs are these two dots. This is the gas emission. But actually what they infer from, Pineda et al. Infer from the modeling of this disk, of the continuum of this disk, is that there may be a truncation of the disk more or less at the same distance of the planet. So obviously, this is a disk that should be followed up with Alma now that there are the longest baselines and higher angular resolution is possible. So there are a lot of things that are almost within our grasp with Alma, and I'm sure that cycle 3 and beyond will offer a lot of new results in these areas. Okay, let's go to the debris disk very briefly. I don't have too much time to spend on this. So what are debris disks? This is debris disks were discovered essentially by IRAS in their original thing. The first thing that you do with the telescope when you want to, you try to calibrate, and so essentially they looked at Vega, which is our standard star, and they found an enormous excess, and excess emission at long wavelengths. And these are the 4 disks that were originally found at the beginning of the IRAS mission, because they are the most prominent, and they are all around main sequence stars. So there is Alpha Lyrae, Vega, then this one is Fomalhaut probably, this is Beta Pictoris, and this is Epsilon Eridani, okay? And you see basically that these are the original plots, so excuse me for the terrible thing, but this is the photosphere as you would expect it, and these are the measurements in the far infrared. we show that all these objects have excess emission at 100 Kelvin, 100 microns, roughly speaking, and they were modeled with an emission from dust at several tens Kelvin temperature, okay? These disks are thought to be secondary disks, so they are not thought to be the primordial disks, but rather dusty disks produced by the collision of larger bodies inside the planetary system that is around these objects. That's because the lifetime of these structures around these main sequence stars is very small, because you tend to blow away essentially the dust by the radiation of the wind and the radiation of the star, essentially. Okay. These are some more recent images of what was called the fabulous 4 debris disks. And you can imagine that somebody was, even a generation before mine, decided the name, of course, because this is the Beatles. It's basically, these are the 4 disks that I showed you before. IRAS just detected the excess, and these are the image at 70 micron from Spitzer, in which basically you see that you start resolving some of them, and these are the 850 microns image from, actually this one I believe is 450, but anyway, submillimeter images from the JCMT of all these objects that show essentially the dust distribution around the star, essentially, okay? If you compare these disks with the classical disks in terms of the amount of material that they contain at this stage in dust, this is what you have. These are the debris disks, okay? There are more than the few that I showed before, obviously, and these are the classical disks. So the classical disks, the one that we have been discussing so far, have masses that are in this unit. This is mass of dust, okay? So in these units are hundreds of solar Earth of mass, and then these debris disks fall down by almost 3 orders of magnitude, essentially, immediately, okay? So there is a big difference between the two. And the age difference is not dramatic in the sense that, there is an overlap in ages, more or less, between the old classical disks and the young debris disks, okay? So one of the puzzles, if you want, is that, or the interesting aspects, is that we don't see a continuous transition of this, and there may be several reasons. One reason might be that, well, we are not yet sensitive enough to detect in these young star-forming regions these debris disks, because they are far away. And the other reason might be that the evolution is very fast, so the disk disappears, as we have been saying already yesterday. The disk disappears very quickly, and then you form this secondary disk in a separate way. Okay, this is Herschel Observations of Beta Pictoris with a nicer spectral energy distribution, although no, this is not a spectral energy distribution, this is just flux density, so it's not multiplied by the wavelength here. So this is the star, and this is the excess measured, and you see is slightly resolved at 70 micron, but really not resolved at the longer wavelengths. And these are the Alma images of the disk. Of course, Alma, this is the continuum, it has been rotated a little bit, okay? This is the Alma image of the continuum, and this is the molecular gas in CO221. So as you can see, Alma resolves very nicely the disk, and in fact, all the debris disks that are large enough to be resolved that have been observed with Alma show a dust distribution that is very thin, very narrow normally, the rings. And in most cases, actually, they don't show the gas, but in some cases they do. And this is one of the cases in which they show the gas. And the gas is even more difficult to understand than the dust, because in this type of systems, the gas has a much shorter lifetime than the dust, because the central star gets rid of the gas very effectively in these optically thin disks, okay? The disk is optically thin throughout. The other thing that you notice is that the gas is not symmetric, but is asymmetric on one side. So there is a clump of gas. And this is essentially the deprojection of this disk that is seen at on a face-on view, based also on the kinematics of the gas. So this is the reconstruction. And there is some uncertainty on the near far side. This is their preferred model, but this is also possible in terms of reconstruction. And the thing essentially that you see is that the gas is concentrated in a very small clump overall compared with the rest of the disk. And the interpretation is that, again, in these collisions that produce the dust, then if the two bodies that are colliding are icy bodies, then you release also the gas. And the dust has a longer time scale, so it creates a ring, essentially. It creates a full disk, while the gas has a short lifetime, so it stays there only for a short time after the collision and localized in the region where the collision happened. Okay. Let's see. Yes, one of the things that are interesting at this point of view is that if you estimate how much mass do you need how large these bodies have to be to do this, to produce so much gas, essentially, they have to be fairly large. I don't remember the exact number for Beta Pictoris, but typically for the debris disks that have been observed, the rule of thumb is that you have to destroy one full large comet every half an hour, roughly speaking, okay, as a rate to explain the gas that is observed. So the amount of collisions is fairly high. And this opens the possibility of studying the composition of the ices in these objects, because when you have the collision and you produce this gas, then for some time you have the gas available for directly probing the composition. So this is something that certainly will come up with Alma. Obviously, this amount of gas is little, so you need a lot of sensitivity, and Alma is the only instrument that allows you to detect properly and measure the isotopic abundance, for example, of this gas. This is something that will be coming. Okay. I'll stop here and get the 5 minutes, and these are my two topics for the 5 minutes, and yeah, okay. Yes. Yes.
By Alma.
Yes.
And you see the Alma
CO221, yes. 322.
Yeah, and different risk usually, according to what I read, our understanding is usually most of the material is
It's just dust, yes.
just dust.
Yeah, the amount of gas is very low. The amount of gas is very low, and Beta Pictoris was actually detected before Alma, the molecular gas. So there were a detection of molecular gas, I believe with the JCMD, but there was a detection of molecular gas. The thing that Alma repeated is that many disks actually do have some gas solution, but the gas is very low, so it cannot be detected without detection. That's why it was not known before. There is some gas.
mass of the main belt drop with the orders of magnitude after the least stability.
Yeah, could be that something like that. Icy bodies, so that's why we say comets, no? Because comets have the ices, and so that's the related to the bodies that contain both dust and gas and ice. Yeah, no, just finished. Okay, so the.
We have to recap each slide.
Oh yeah, no, don't worry. Okay, so the 5 minutes are up. So I'm sorry, the first one was not phrased as clearly as some of you asked me, as I meant. I mean, I meant here the drop in mass. So this sudden jump of 3 orders of magnitude in mass from the classical disks and the debris disks. And well, the few of you had the idea that there might be different processes going on there, and one of the ideas was that, for example, well, what if the ages of these stars are wrong? So, they are not overlapping in age. So let's go back to this plot. What if this axis is wrong for these stars, and actually these stars are not here but there? Then it could be a normal fall off. That's always possible. There was a long discussion in the literature on the age of Beta Pictoris itself. And the range of ages quoted in the literature go from 10 million years, so a very young, relatively young object, to over 200 million years. That would put, yes, Beta Pictoris here, so that would be... So one of the way in which this was discussed is that Beta Pictoris is not a totally isolated object. It looks like it's isolated because it's nearby, but it's part of a moving group, what is called a moving group. So there are a set of stars that have a common absolute motion compared to the sun, okay? And so it's a sort of a small association that is expanding and moving in space. They are not close by when you look at them in the sky, obviously, like a cluster, but they have a common motion, a common distance. And looking at all these stars, which have different masses and fitting again, evolutionary models, I think the best estimate of the age is now accepted to be between, say, between 10 and 20 mega a year. I don't remember the exact number, but still on the young side, okay? And similarly for a number of the other debris disks. So I think that it's true that there are some that are here, that are at this age, and there is a sudden drop. Okay. The other thing, on the other hand, is that the debris disks are all close by because they contain so little dust. The excess is so small over the photosphere that to detect it, you had to be very sensitive. And so, now with Herschel, they have been trying to expand the samples, but still the nearby star-forming regions are not really probed at this level of sensitivity, okay? And even with ALMA, if you want to reach this sensitivity, so 3 orders of magnitude below the sensitivity of the typical disks, it's not easy. It's a big investment. So there are some programs. We have been trying to detect some maybe debris disks around the so-called class 3s, so the disks, the stars that are without disks in nearby star-forming regions, but the sensitivity limits are still in between the 2 samples, if you want. So we cannot really constrain very much yet this difference, nor we can constrain how much, so when it starts, how big is the difference, and whether all stars go through this phase or only a small fraction of it. Another idea that was interesting is that if you think about our own solar system had this very highly dynamical phase in which there was this movement of Jupiter and Saturn that created a lot of collisions at a certain point, the Nisor-Grantak model. And at that time, probably, there was also the creation of a lot of dust. So it might be that some of these objects could be in that phase. If I remember correctly, the NISP model expects around this age here to have the big late bombardment on Earth. Okay. So the reason why we don't see this in star-forming regions is that we still don't have the sensitivity to do a survey and just see them, okay? We still have to do a lot of investment of time, but this is something that will happen, and we will have a more clear idea of this evolution in the future. So the take-home point for what I said so far is that, well, the results from ALMA are coming, and there are a lot of programs on these evolved disks, and basically which connect on the early evolution of the planetary systems that have been already formed, and will arrive fast. The other aspect is that the boring disk will be resolved soon with ALMA, and I'm sure that in the coming year or two we will be looking at perhaps at bananas in boring disks. I don't know. I mean, these asymmetries maybe will be there also in boring disk. Okay, and the detection of the molecular gas is a particularly interesting thing in debris disks, at least to me, because it allows you to probe these ices in the outer disks. Okay, I now want to change topic to some extent and talk about environmental effect. Instead of talking about environmental effects in an abstract sense, I thought I would connect with the solar system and trying to think whether the solar system is completely consistent with the picture that we have discussed so far. So far, we have all discussed, all 3 of us has discussed the evolution of these disks in total isolation, the formation of a star, a disk around it, and the formation of planets in this disk, forgetting about almost everything except for some dynamical effects. This may not be the case for most, well, this is certainly not the case for most stars, because most stars form in groups and clusters. But it may also not have been the case for the sun, that now is isolated, but maybe it was not when it formed. So this slide comes from the first day, and is on the radioactive decay, isotopes decay, and in particular, what has attracted a lot of discussion in the literature are these 2 isotopes, iron-60 and aluminum-26. As I said, the first day, the aluminum-26 can be formed in supernovae or in the winds around Wolf-Rayet stars, so the winds around massive stars. And it may have an internal process, so a process meaning that the sun, the high energy radiation from the sun, could have produced a small amount of this isotope in the disk by essentially interaction between radiation and matter. This is thought to be not very relevant or not able to produce the amount that is observed. So you are left with these other 2 causes. So somebody else throw into our forming system aluminum-26. So this is an environmental effect to some extent, okay? We didn't have this, and this arrived to us somehow. Even more so iron-60, because iron-60 is very difficult to produce, and essentially you produce it copiously only in supernovae, okay? So basically, the idea is that, well, and since both of them can produce in supernovae, one idea that was in the literature for quite some time is that while you were forming the sun, a supernova exploded in our backyard, and all this material arrived in the disk. This doesn't really work because the amount of iron-60 over aluminum-26 that you produce in a supernova is so high that we would expect to have much more iron-60 than aluminum-26 in our own system, while it is the opposite. I mean, okay, the aluminum-26 was more abundant than iron-60. So there were a lot of different ideas running, obviously. So you start, since one supernova is not enough, then you start to complicate and you think about the effect of a cluster of stars. A cluster of stars has the advantage that has a set of stars of different masses, as one star that is very massive, perhaps, and do a supernova, produce iron-60, and a lot of stars that are less massive, don't do a supernova, don't produce iron-60, but produce aluminum-26. So if you get these two things together, you can possibly get a mixture which is relevant for us. So one of the models that was discussed quite a bit in the literature is that you have a cluster that is forming that contains massive stars. This cluster evolves. Some of these stars become Wolf-Rayet and start to pollute with aluminum-26 the molecular cloud around the region where the cluster is, and aluminum-26 and iron-60 if you have a supernova that explodes. And then at some point, you have the collapse of this material. At some point, but relatively quickly, you have the collapse of this material, you form another cluster or a single star, the sun, and you are there. So if you run this type of simulations in a Monte Carlo way, you discover that in this case, you are still dominated by the iron-60 production. So essentially, your model would predict these ratios. You predict less iron-60 than aluminum-26 as you wanted, but still to predict the sun, you need to be in a very improbable situation. And obviously, we all don't like the anthropic principle, so all of us would like to be in the most probable situation. So we think that this maybe is not the explanation. Another possible explanation that has started that has been discussed very recently is this idea that molecular clouds, since these molecular clouds are very dynamic, you have continuous star formation episodes. So this is a variation in some sense of the previous one, but the difference is that you have this continuous stars forming, exploding, stars forming, exploding, and so on and so forth. And so with this process, in molecular cloud, if the sun forms in a molecular cloud that is, say, between 10 and 20 mega-year old, or material that has been going through this process for 10 to 20 mega-year, then you predict the correct ratio of aluminum-26, essentially. You still overproduce the iron-60 because you see here what they are simulating. This is the density of the gas in the cloud as a function of time. This is when the supernova exploded. This is after 1 mega-year. When the supernova explodes, it creates a lot of iron-60 and aluminum-26. This is the aluminum-26 that then gets mixed with the rest, and actually it's concentrated in the high density region. So that was the idea behind all this model, but still you have too much iron-60. Another possibility is, again, is connected with this, so is a refinement of this type of model, is that you have a first generation cluster with in a molecular cloud with massive stars, say. Then some of these massive stars explode, and they pollute the molecular cloud with iron-60 and aluminum-26. But aluminum-26 has a shorter decay time than iron-60, so aluminum-26 is removed, and iron-60 goes down. At a certain point, you form a second cluster, which contains, again, massive stars and produce aluminum-60. And the sun is part of a third generation that incorporates the iron-60 from the first generation, from the first cluster, and the aluminum-26 from this second generation. If you run this model and you ask yourself how large these clusters need to be, how much time do I need between the various phases, this is more or less consistent with what we know of star formation in big, huge complexes in which you have multiple generations of clusters forming in these clouds. So it's not completely unreasonable nor completely ad hoc. The thing that you find also is that the typical size of these clusters is of the order of few thousand stars up to 10,000 stars. Maybe this one has to be a little bit more massive, so more members, because it needs to have a 30 solar mass, at least supernova, to produce the 30 solar mass star, that then when it goes supernova, it produces the iron-60. Okay, so this is consistent, and if this is the real situation, then I mean all stars essentially that are in the stars that form in this type of environments would be very similar to the sun. You may ask, where are all these stars now? Because the sun is alone. Well, in the 4.8 billion years since the formation, obviously these clusters have dispersed. The various stars have different orbits around the galaxy, and you do expect to have erased the memory of the nearest neighbor around you, especially for clusters of this size. Okay, so do we observe these interactions between clusters and star formation? Yes, we do. This is an example of the famous M16, where you have a massive cluster here that is forming and is basically interacting with the cloud around it, and you see this is the famous so-called pillar of creation that contain dense gas that is interacting directly with the stars. The thing that is still debated is how much this is a fertilization versus a sterilization, okay? Because it's not that obvious that in this situation you are actually mixing new material with this one and form new stars. If I mean, we have been, the student has been observing this thing with a new instrument at the VLT that allows you to do this 3D imaging also in molecular in optical lines, so you get also the velocity of the gas. And what you basically see is that most of the effect that these stars are having on these pillars, these are these three, so the dark things are, say, dense molecular material, and what you see here, most of the effect is the fact that this is being photo-evaporated, so rather than putting stuff into the molecular clouds, you are getting stuff out of the molecular cloud, and it's not that obvious that you form stars. There are a few young stars. There is one here, so maybe, but it's not an obvious thing. Nonetheless, it's possible that the sun has formed in a cluster environment, and another reason to think this. Let's see if I had it. Here. No, I don't have it. One other possible reason for this is that the fact that there are some evidence, some indirect evidence, that the outer region of the solar system have been influenced by gravitational interactions, because we have a surface density of material in the solar system that drops drastically at 30 AU. So after Neptune, there is not much. The mass that is in the Kuiper belt is very small, and this is different from what we observe in protoplanetary disks. The protoplanetary disks have a much shallower distribution normally, and the other reason is that the orbits of some of the Kuiper belt objects, in particular Sedna and another one that I forgot the name, are consistent with being influenced by some gravitational interaction with some other body outside. Okay, so there is a possibility that the solar system formed in a cluster. Is this sensible at all? What is the fate of disk in a cluster environment? Okay, can we have a solar system formation in a cluster? Obviously, it depends on the cluster. That's obvious, no? So, but let's focus our attention. I say the few thousand stars. Few thousand stars is the Orion Nebula Cluster. Is it possible that we form an Orion Nebula Cluster? If you look at the disk properties in the Orion Nebula Cluster, you all know, I suppose, that the disks that are very close to the center of the Orion Nebula Cluster, this is the trapezium, the 4 stars in the Orion Nebula Cluster. All the disks that you see here, these are the continuum submillimeter 850 micron images of these objects. So there is a disk, but they are heavily photo-eroded by the radiation. But this is not true of the disks that are a little bit on the periphery of the cluster, okay? This is true only of the objects that are very close. And in fact, if you look at the distribution of the mass of these disks measured by Alma and SMA as a function of distance from so it's again, this is millimeter photometry as a function of the distance from this star, which is the source of the energetic radiation here. You see that the disks that are close by have very low masses, so they are much below the minimum mass solar nebula. So it would be hard for us to form there, even if we would survive. I don't know. But if you go outside the cluster, okay, in the outskirts of the cluster, then the properties of the disk are actually quite consistent with the disks that, for example, are in the Taurus molecular cloud. So it's plausible that if you are born outside there, and then you have your mass and you are not affected by the photoevaporation directly. Another effect when you are in a cluster is that you have dynamical encounters, not only photoevaporation. So one thing that one may ask is, well, what's the survival time of the outer disk in a cluster environment? This has been looked at by many people. This is just an example, actually, for a star that resides in a cluster for a long time. So it's not the case of the sun. But basically, you see that you need to go into a situation in which to survive for a time which is as long as the age of the solar system, with a planet that is as distant as the Earth from the sun. In these clusters, basically, the surface density of stars need to be less than 100 stars per parsec, I believe, which means that in an environment like the core of the Orion Nebula Cluster, you wouldn't survive because it's 10 to the 3, 10 to the 4, okay? So you need something less to survive in those environments. Okay. If you put together, this is putting together all these constraints for our own solar system. So putting together the constraints on the isotopic things and the fact that we need to be in a cluster that is not so massive, otherwise we have too many dynamical encounters, and also folding in the probability of how many stars are found in clusters. So there is the peak of the probability for us is to form, again, in a cluster of a few thousand stars. Okay, this is from a review by Fred Adams in the Annual Reviews. If you are interested, it explains all the possible things there. So I think there is, obviously this is still debated, but there is a good fraction of the community that thinks that the most probable explanation for the sun is that we were formed in a moderate cluster, okay? So in something like this one, okay? So this is M67, and this is how it appears today. It has approximately 500 stars. It has the same age of the solar system. It is the cluster with the metallicity in the star which is closest to the metallicity of the sun. The only problem is that it has a completely different orbit in the galactic potential. So it's not obvious that we could really come from this cluster. But this is a serious possibility, and there is a discussion of this in this review if you are interested. There are possible ideas how you could change the orbit of the cluster. One of the problems is that this cluster has an orbit which moves very far from the plane, okay? So as a high scale height from the plane of the galaxy, I mean, okay? While the sun is right on the plane of the galaxy. And so it's very difficult to think that we started with an orbit that was very far from the plane of the galaxy, and then we kicked the sun on the plane, because that would have had big dynamical effects on the planets. And so the idea rather is that the cluster may have been scattered through an encounter with a molecular cloud off the plane, essentially. Okay, but this is just an idea. One thing that still needs to be explored in detail, I think, is how, because so far you have seen the photoevaporation from a bright central star, and you have seen the dynamical interaction as two separate problems. What still needs to be investigated in detail is the combined effect of all this, so having the dynamical evolution, the external photoevaporation from massive stars, and the internal photoevaporation from the stars and from nearby stars when you have a close encounter. This is being explored now. It's not an easy problem to explore. This is a test, actually more just a proof of concept of how one can do it, of a simulation of a small group of stars, 100 stars, which start with a disk, and then it evolves dynamically, and as you evolve, there is both photoevaporation and dynamical interaction. And so you see all this color that is getting up. This color is essentially material that was in the disk and is being stripped and diffused into the cluster by the encounters between the stars. So I think that at the end of the simulation, they don't find too many problems for the stars for the disks to survive substantially, so to form planets where we have planets. But this is a very ad hoc setup at the moment. So they are 100 one solar mass stars with 0.1 solar mass disks, and they're all the same, and there is no real exploration of the parameters. It's just a proof of concept. But this is something that will be interesting to explore in the future. And what would be interesting from the observational point of view is that all these scenarios can be tested. I showed you this test of the masses of the disks in this Orion complex. Obviously, you can test these dynamical scenarios here by looking at different clusters of different densities, because basically what you have here is the mass distribution of disks for populations in different clusters. So you can do this with Alma now, and this is something that probably will be done. It will require still some time, but will be done. Another interesting aspect, which is the last one that I want to cover very briefly before telling you 2 words about Alma, is that if you think that we were born in a very complex environment, as I said at the beginning, with several generations of stars, several molecular clouds, and so on, what happens is that exactly you have young clusters, molecular clouds that will form stars afterwards, and a distributed population of not so young stars. Okay? So why I'm saying this, apart from showing this beautiful image? Because the interesting thing that has been discovered recently is that if you look at this population of old stars across this region, old here means not really old, means older than this disk dissipation timescale. So it means 10 to 50 million year old. Huh? So they should not have a disk. They should not have a disk, but there is a large population that shows H-alpha excess. So they are accretors. They accrete, and they accrete from what? They must have a disk around to accrete. Okay, so that's the reasoning. If you compare this population with the population of the cluster, here in blue are H-alpha emitters, so stars that accrete, that are young and in the cluster, and in red are stars that show H-alpha, so they may be accreting, but they are not concentrated in the cluster, and they are older based on the HR diagram. And the spatial distribution is different. You see that the blues are clustered, the red one are all over the place. So they are consistent with being an older population. Okay? They were first discovered in this environment, the 30 Doradus region in the large Magellanic Cloud, which is again a huge complex, where you have the cluster here. And again, you see all these stars that show significant accretion in some cases. The interesting thing is that again here, you have a molecular cloud which is observed by Alma, and Alma has shown that has a small-scale structure like cores and clumps that may form stars in the future. And the question then is how you get a disk around this thing. And one possibility is that simply these stars have disks that live for 50 million years old, but this is really unpleasant because there is not so many that should be there. The other possibility is that they have reformed the disk. And how can you reform the disk? Well, one easy way to think about it is that you have a first generation of star that forms in a molecular cloud with their own disks. This generation evolves, carves a hole, destroys the molecular cloud around it. The stars start to lose their disk. The disks are less and less because they are evolving over this 3 million year timescale. On another portion of the cloud, by the way, you have another core that is producing a newer generation. So this is a generation new with their own disks. And then what happens? Then happens that these stars, since they are moving, they have a velocity dispersion, typically these stars of the order of 1 kilometers per second. They go through the cloud. Some of them go through the cloud, and they may go through a dense core, and at that point they may reaccrete by Boyne-de-Hoyle accretion material and recreate a new disk. So you may have a situation like this one in which you observe a young cluster with its own disks, and then an old population, some of which have reaccreted a disk. Is this sensible? Does it make sense? Well, it depends a lot on two parameters. The key parameters are the dispersion, the velocity dispersion of the stellar population. The fastest they are, the less they accrete, obviously. But the slower they are, the less chance they have to go through the cloud and get a dense core. And on the clumps filling factor, the filling factor of the dense material in the cloud. If you plug in reasonable numbers, so 1 kilometers per second, and filling factors of the order of 10 to the minus 3, 10 to the minus 4, you discover that this is the cumulative fraction of stars that have accreted that much mass, and this is the fraction of stars at any given time that show an accretion rate due to the disk that they have reformated through this process above a certain threshold. And you see you can have a few percent of stars, 10 to the minus 2 here, few percent of stars that accrete to 10 to the minus 8, 10 to the minus 7, which is what is observed, and a cumulative fraction of, say, up to 10%, I would say, of stars that have accreted, as much as their original disk. Okay, so this is not a totally impossible process. It may happen. What this implies in terms, if you had a planetary system around and you are reaccreting a disk, the mess that you create is not obvious. So it's not obvious how much it will survive, but this is a process that could happen in some cases. Okay, these are my take-home points, basically saying that it is possible or even plausible that the sun has formed not in isolation, but in a cluster, and so the evolution of disks and in clusters and the effects of a cluster on a disk are important. The last thing I say that this is standing, and I want to go to the glacier, so I want to finish early. But so I have my own motivation. But one thing that I want to say is that there is Alma coming up, so I thought I should, Alma Deadline coming up, so I thought I have to show you something. So I grabbed this view graph from a recent talk that I gave somewhere else, and basically telling you that next week there will be the call for proposal coming out with a deadline towards the end of April. Getting Alma time is not the easiest thing that you can think of because there is this crunch at some point of the order of factor 5 to 10 that reduces, because of the oversubscription rate, but it's not so terrible. Any space project has the similar oversubscription factor, so people should apply. And as I always say, the best way of not obtaining time is not to apply. Then you are sure that you don't get time, okay? So one should try. What will be possible? The key capabilities are this one. This cryptic band 3, 4, 6, and so on means that we will observe at the wavelength that goes from 3 millimeter, 1 millimeter, well, to 1, 850 micron, and so on, up to 350 micron. Okay, so the range of wavelengths will be that. We will have the good collective area with 36 12-meter antennas, most likely, and baselines up to 10 kilometers in the short frequencies, and up to 5 or 2 kilometers at band 7. This is significantly less than what we used for the HL tau image, okay? So we will not be able to get to the angular resolution of HL tau in this cycle 3. This will probably come in cycle 4, but almost there. The other thing that I wanted to say is, yes, that some of these observations will be in shared risk mode, but you will have all your help from your local Alma regional node, and you should make use of that. Somebody asked me on the future capabilities of Alma, the medium and long term. So in the medium term, or short term, medium term, we want to get to the long baselines. We already are going into intermediate baselines now in cycle 3. In cycle 4, we will do the 15, 16 meter, 60 kilometers baselines. Sorry for the lapsus. And then what the other things that we want to implement are the full sensitivity, we are almost there, and efficient spectral scans for basically doing broadband spectroscopy. And also the chemistry of complex organics and water. Somebody asked me, when will the water receiver be available? We are commissioning it now. So we have started commissioning the first of these receivers, and we expect to offer it not in cycle 4, but in cycle 5. Okay, there will be most likely next year a call for science verification. And finally, the last thing that we will do in the short term is the VLBI. Where is it? The VLBI, to look at the event horizon. It's not really useful for us, but just to let you know. And we will look at the sun. Okay, cycle 4, the sun. Unfortunately, we missed the eclipse, but cycle 4, we do the sun. On the longer term, we have something that doesn't fit anymore in my slide. Yes, okay, it's coming. But we have a development plan that will deliver a number of improvements, including the low-frequency receivers toward the end of the decade. And the low-frequency receivers will be important for us as a community of disks for 2 reasons. The first reason is that we go to longer wavelengths, and so we probe better the dust evolution. And the second reason is to go into longer wavelength, we probe the low excitation heavy molecules, so the deuterated and complex organic molecules. Okay, sorry for this additional 5 minutes. Stop here.
Okay, thank you, Leonardo. Questions?
Thanks. Leonardo, I'm curious to get your opinion on the scenarios to get the right levels of enrichment to find 60 and only 26. Multiple generations of star formation. Would you not expect there to significant age spreads in quite compact star formations?
No. That's an important point. So what you expect here is you expect to have basically a difference between the various generations, the separation in age between the various generations of 5 million years. And each generation is expected to be the standard 1 to 2 million year spread. Okay? So it's not different, for example, from what you see in Orion. In Orion, you have the Orion Nebula cluster at 2 million years. You have the Sigma Ori cluster at 3 to 5 million years. You have the Orion OB1 and so on groups that are 10 to 15 million years. So each of these groups individually has a small age spread, and that's fine, that works. But then you have subsequent generations that goes, you have older generation of stars in front of your younger generations. So that's the idea behind this. It's not mine, Guinel and Mainet. Yeah. Yeah, so those are mine, in fact, yes.
Yeah, okay. I was wondering, okay, when you have these stars going around, they all have the disk in the same direction.
No, that's my cut and copy paste thing on this diagram. Sorry. Sorry. I wasn't smart enough to rotate. No, I didn't meant anything profound with that, no.